have done this experiment before, and so what I was trying to think of was an activity that you could take back to the classroom and teach your students a little bit about viruses and genetics. Okay, so a little about me was I actually got my undergraduate degree at West Virginia University in Morgantown, and then I did graduate work at Baylor College of Medicine in Houston, so I have a PhD in virology. And then I moved to the University of California at San Francisco, and I worked with Nobel laureates Mike Bishop and Harold Varmus. And then I moved to the McCardle Laboratory for Cancer Research at the University of Wisconsin at Madison. And then I joined the faculty in Austin in 1983. And so I've been teaching at UT for 34 years. And I've taught probably 2,500 undergraduate students. And then I have a research program on studying viruses, particularly retroviruses. So you all know retroviruses as the cause of AIDS. But also retroviruses cause a lot of other sorts of diseases, including cancer and arthritis. And so what I thought that I would do is, this is we won't play the whole movie, but this is a short presentation that I think tells you a little bit about viruses, and then we'll move into the activity. Okay. You have to use the keypad. You have to use the keypad? Yeah.
Your hands, because a sign of discovery is about to be invaded by submicroscopic parasites in Understanding Viruses.
In Viruses and Illness, you'll learn how viruses range from the common cold to HIV and have caused epidemics of disease more decimating to humans than any war or natural disaster.
We'll explain how viruses operate and how your immune system works to defend you. Then we join scientists making radical new attempts to use invading viruses as agents of healing.
Finally, in fighting disease, we'll see how science is leading the war against the cold and flu.
The volatile world of viruses, coming up next.
As you watch the first part of Understanding Viruses, keep these questions in mind.
How do viruses reproduce?
How did World War I contribute to the influenza pandemic of 1918?
Living creatures are susceptible to attack from a wide range of viruses. But our first step in combating them is knowing what they are and what they do. What kind of viruses do you know about?
Cholera, diphtheria, measles, mumps.
The flu, hepatitis, AIDS, SARS.
So T cells, and I guess HIV destroys those, and so you don't have an immune system.
AIDS, herpes,
Well, the West Nile virus.
chickenpox, polio, whooping cough.
SARS, computer viruses attacks computers.
You get cholera, you have diarrhea, and you die.
This team of Army medics is rehearsing, not for the outbreak of war, but the outbreak of virus. It's a battle where shaking hands can be more lethal than dodging bullets, where the adversary numbers in the billions, where nothing is constant except the potential danger. Viruses are things on the very edge of life. You can't taste them, smell them, or see them, but they're there. In the air, in the water, in every living thing on the planet. They're the tiniest, simplest forms of life on Earth. Yet they have ways of entering our bodies, kidnapping our cells, and outwitting our immune defenses. Viruses are old. Some believe they're older than all other forms of life, and they are patient. Without a living cell to invade, they wait in a crystalline form somewhere between life and death. Some can wait for centuries. Their only goal is to reproduce. Viruses are pure purpose.
Viruses, when they're out there in the environment, are basically just pieces of genetic information wrapped up in a protein code or some other little bit of protection, vulnerable to all the elements in general, and just waiting for the next living thing that they can grow in to come along so that they can infect and propagate themselves.
It's the form of life that cannot subsist. It doesn't have the machinery with which to live. It can only do so by entering and utilizing another cell for that purpose.
And when it uses human cells for that purpose, we usually end up the losers. Diseases caused by viruses are as potent a force in the history of humankind as war and natural disasters. Influenza, 15th century Italians called it that because they believed it was caused by the influence of stars and planets. Smallpox was first reported in Chinese literature 3,000 years ago. There are 7 different kinds of herpes. Chickenpox is one you might have had to deal with. Kuru is found only in cannibal tribes in New Guinea, transmitted by eating human brains. Each cold you get may feel the same, but it's not. There are hundreds of different cold viruses. In your lifetime, at least 50 cold viruses will catch you. And the list goes on. As common as colds, as deadly as AIDS.
Viruses are a cause of a lot of misery. There's the viruses you catch in the office, the daycare center, that your kids bring home from school, that cause minor disease. We don't diagnose viruses specifically, so that we often pass them off and we don't pay the kind of attention to them that we might.
Viruses have always been difficult to pin down. Even the most powerful optical microscopes could only magnify objects 2,000 times. They revealed a watery world of bacteria and single-celled creatures, eating, moving, multiplying. What they couldn't see was the phantom that destroyed cells with stunning efficiency. Then in the 1930s, German scientists invented the electron microscope and could finally see a virus at 7,000 times magnification. Instead of bouncing clumsy light waves off objects, it used tiny electrons to magnify. One look through the electron microscope instantly changed how people defined the boundaries of life. They discovered organisms so small that billions and billions of them could fit into a single pixel on your television screen. Scanned by electrons, viruses were revealed to be spheres and spindles and geometric shapes. They looked too symmetrical to be alive. On today's supercomputer screens, viruses look like ornaments from a Martian Christmas tree. This is the AIDS virus. Its core contains the genetic information necessary for the virus to duplicate itself.
It's a package of nucleic acid, of genetic material, enveloped in a set of proteins that allow this virus to utilize the cell for its own replication, because it cannot function independently, it cannot multiply independently.
The genes are protected by a thin shell. The shell is studded with molecules that enable it to dock with a target cell and work its way inside.
There's some receptor mechanisms that come together, they attach, they don't attack, they attach, they're incorporated, and they use the cellular mechanism for its own multiplication. It acts as a parasite. It uses these organized systems for its own survival.
The target cell doesn't have to be human or even animal. The tulip break virus has been used since the 16th century to cause color variation in ornamental tulips. Nothing is too small for a virus.
So, naturalists observe a flea, and smaller fleas that don't prey. And these have smaller fleas to fight them, and so proceed ad infinitum.
Yep, even germs can get germs. An example, the T4 bacteriophage, a virus that attacks bacteria. It lands, hooks on, and pushes its DNA through the cell membrane. Once inside, the viral DNA hijacks the cell and forces it to make more viruses. Within minutes, the swollen cell explodes, releasing hundreds of new viruses to infect other cells. In ancient times, people didn't know about viruses, but they did know this. Getting sick was the last thing most of them ever did. Where did these diseases come from? Was it the wrath of the gods, omens, sorcery? The plague that struck during the Peloponnesian Wars in the 5th century BC may have been typhus or scarlet fever, or it could have been measles. Smallpox was the scourge of the Middle Ages, killing many and leaving survivors permanently disfigured. When 20th century archaeologists opened Egyptian tombs, they found references to what could have been polio. But diseases of the past were limited in time and space. The world had not yet experienced viral epidemics on a global scale.
Did you know viruses are highly specific? Rabies targets the brain. Different cold viruses attack cells lining the nose and sinuses. Mumps infects only the salivary glands. Hepatitis settles in the liver. Viruses are the biological equivalent of smart bombs, and cells have been their targets for thousands of years. One of the worst natural disasters in recorded history was caused by a virus. The influenza pandemic of 1918 struck every major U.S. city, dropping people where they stood.
There were at least 20 million people killed worldwide, and it's probably the worst pandemic the world has ever known. There were more people killed from influenza than there were from the First World War.
The war itself was the problem. If there had been no war, that year's strain would have stayed isolated. But when Allied troops met in northern France to exchange fire with the enemy, they also exchanged a lethal strain of flu. So it began.
It then went from France to the United States, and it disseminated from Boston.
At Fort Devens, Massachusetts, one case of flu turned into more than 6,000 cases between September 1st and September 18th. It took only 17 days. lost nearly 4% of its population. Alaska, 8%. In the South Seas, the death rate was 20%.
People were absolutely panicked because somebody could be playing bridge one night and they would be dead the next day. And so they did all kinds of things. They were wearing face masks, and in fact the police all wore face masks. They were carrying little pouches of garlic and onion, just anything that they thought would protect them from the flu.
They had no idea that they were leaving exposed the very place where flu enters the body, their noses.
Nothing was known about how to cope with it. And that is something that began to emerge when we got into the 1930s, 1940s, 1950s. By that time, there was enough knowledge and experience and the development of techniques to make it possible to proceed.
Never before in history have doctors been able to do so much to preserve your health as they can today. And almost everywhere in medicine, the parade of advances that will benefit countless millions has just begun.
Vaccines became a scientist's dream. They promised to rid the world of viral disease. Curiously, the word vaccine comes from a cow disease called Vaccinia. In the 18th century, the beauty of milkmaids was a cliché. They alone seemed to be spared from smallpox. An English country doctor named Edward Jenner observed that a surprising number of milkmaids caught a mild, measles-like illness called cowpox, known officially as Vaccinia. Jenner extracted the virus from blisters and infected a child, his own infant son. Then, he inoculated the boy with live smallpox virus. It was shockingly risky, but it worked. The initial cowpox injection did cause mild sickness, but it was enough like smallpox that his body eventually built an immunity to both diseases.
We have evolved our own defense mechanisms over the years. We know this is the immune system, which is a very complex system containing many different kinds of cells and functions, whose major purpose, by and large, is to recognize what's foreign and attempt to rub it out.
The immune system has three major functions which are working in your body right now. Antibodies are proteins that bind to the surface of a virus, flagging it for destruction. The body's white cells move in to destroy virus-infected cells. Once you have been infected with a virus, memory cells will immediately recognize it if it enters your body again. This is why vaccines are so effective. The body remembers what the fake virus looks like, so it can protect you when the real virus comes along. One of the most common ways to make a vaccine is to grow it in an unnatural host. Chicken embryos are used to grow human viruses like yellow fever, measles, mumps, and influenza.
Influenza has been grown in eggs for many, many years. It's our standard way of producing virus. It can also be grown in tissue culture and grows very well in tissue culture, but you can't produce enough tissue culture to make large doses required for industrial use.
Every year, flu virus is injected into eggs. After several transfers from egg to egg, the virus will have become better adapted to growing in chicken cells than human cells. When injected into a human, it looks enough like the enemy to cause immunity, but isn't strong enough to cause sickness. The flu virus has found a way around the immune system by mutating, changing the way it looks. Sometimes it changes only slightly. Other years, the change is radical and we are defenseless.
Sometimes you can get partial immunity, which will give you some protection. But when we have what we call a shift, That is usually what occurs when we have major epidemics. Then the immune system doesn't recognize the flu at all. Bears no resemblance to anything the antibodies have seen before.
How much a virus can change depends on how it's made. If it has genetic material arranged in the familiar double helix DNA, then it's pretty stable from generation to generation. In reproduction, when a DNA strand unzips to become 2 DNA strands, a kind of molecular spell checker watches the new molecules form to make sure the 2 copies are identical.
The DNA viruses have a nice copy editing system so they will correct their own errors, which means that the frequency of mutation is low. The RNA viruses do not have those. And this explains why RNA viruses are so variable. These viruses change all the time.
Which is why the vaccine for a DNA virus like smallpox works decade after decade, while every year we need a new vaccine for RNA viruses like influenza. This frozen library is Dr. Herlocker's collection of flu strains that have evolved over the years. These viruses are not dead, just dormant. Each vial represents a different year, a different strain. If you warmed up and breathed flu, vintage 1980, you'd probably get sick. Some vintages of flu are spontaneous mutations. Other epidemics can be traced back to ducks and pigs. They end up with names like swine flu, or the Hong Kong flu, or the Asian flu, because they often come from countries where people live close to their farm animals. Influenza has the added advantage of crossing from one species to the next. Each time this happens, the strain changes. And that means a lot of work for scientists at the World Health Organization and Centers for Disease Control in Atlanta. Every year, it's a race against time.
CDC Influenza Surveillance Laboratory.
Information is gathered from flu watch centers around the world and used to predict what new strain is coming our way. Once this is determined, a new vaccine is developed, hopefully in time.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
How do viruses reproduce?
How did World War I contribute to the influenza pandemic of 19...
Okay, so this is something that's mass-produced, and so there's definitely some errors in this, and you can tell that it's rather old, but some of the basic concepts are still true. So I think we'll go ahead and move into the exercise. And what I had intended for you, everybody should get a sheet of paper. And what we're going to do is to assemble some chromosomes. And then we're going to see how viruses can interfere and interdict themselves into our chromosome. And that's essentially what happens when we get infected with a retrovirus like HIV. So if you want to, I can distribute some of these paper clips. And so if you can get a handful of each color. So we're going to work in pairs.